We live in the age of artificial intelligence. We ask it to write our emails, plan our vacations, debug our code, and even compose poetry. We've invited it into our homes and our offices, treating it as an infinitely knowledgeable oracle. But there's a creeping, unsettling problem emerging from this digital assistant. It's a problem of integrity. Right now, much of what it generates is a sophisticated form of mimicry. It scours the vast, chaotic expanse of the internet, ingesting billions of websites, articles, and forum posts. Then it stitches together a plausible-sounding response. It's a masterful illusionist, passing off what is essentially a homogenized, remixed summary of existing human knowledge as its own original thought. Think of it like a student writing a term paper by expertly paraphrasing a dozen Wikipedia articles without ever truly understanding the subject. It looks right, it sounds right, but it lacks a core of genuine comprehension or originality. This leads to a dangerous digital echo chamber. If an error or a piece of misinformation is repeated enough times online, the AI will learn it as a probable fact. It doesn't question. It calculates probabilities. This is why there's an urgent, almost desperate plea from researchers, ethicists, and philosophers for the next stage of AI development, the creation of a maximum truth-seeking AI. This isn't just about avoiding plagiarism. It's about building a system whose fundamental goal is not just to give a correct-sounding answer, but to pursue the verifiably true answer. An AI that can reason from first principles, that can identify its own biases inherited from its training data, and that refuses to compromise its integrity for the sake of a quick or convenient response. Without this foundation of truth, we risk building our future on a foundation of digital sand, where fact and fiction blur into an indistinguishable haze. But to build such an AI, we need a level of computational power that our current technology simply cannot provide. The AI models that power our world today, like GPT-4, are monuments to modern engineering. But they are also straining at the seams of our current computational paradigm. We've hit a wall of digital sound barrier. Imagine a brilliant, meticulous librarian tasked with reading every single book in the Library of Congress. Our current computers, known as classical computers, are like that librarian. They are incredibly fast, but they are fundamentally sequential. They have to read the first word of the first book, then the second, then the third, and so on, one at a time, until the task is complete. This is the nature of a bit, the fundamental unit of classical computing. It can be a 1 or a 0, on or off, but never both at the same time. When you ask an AI to learn, you're giving it a library of data so vast it defies human comprehension. Training a model like GPT-4 involves processing this library, finding trillions of connections and patterns between words and concepts. On a classical computer, this sequential process is agonizingly slow and astronomically expensive. It can take months of uninterrupted work and cost hundreds of millions of dollars in electricity and processing time just to train a single, large-scale model. We're trying to simulate a universe of knowledge with a machine that can only look at one star at a time. To unlock AI's true potential to build that truth-seeking mind we so desperately need, we can't just build a slightly faster librarian. We need a librarian who can read every book in the library, in every language, all at the exact same time. We need a revolutionary solution. And that solution is emerging from the strange and wonderful world of quantum mechanics. Enter the quantum computer. It doesn't operate on bits. It operates on qubits. And a qubit is where reality as we know it begins to bend. Thanks to a principle called superposition, a qubit doesn't have to choose between being a 1 or a 0. It can be a 1, a 0, and a blend of everything in between, all simultaneously. If a classical bit is a light switch that's either on or off, a qubit is a dimmer dial that can exist at every possible brightness level at once. Now, imagine linking these qubits together. They exhibit another bizarre property called entanglement, what Einstein famously called spooky action at a distance. When two qubits are entangled, they become intrinsically linked. Measuring the state of one instantly influences the state of the other, no matter how far apart they are, whether it's a few millimeters on a chip or across the galaxy. What does this mean for AI? Let's go back to our librarian. A quantum computer isn't a single librarian reading one book at a time. It's an infinite number of librarians in an infinite number of parallel libraries, all reading every book simultaneously. It can explore every possible answer to a problem, every potential pathway in a neural network, all at the same instant. This is why quantum computers promise to train AI models not just a little faster, but potentially millions or even billions of times faster. They could allow an AI to think in ways that are fundamentally different from today's machines, not just processing information, but exploring a vast, probabilistic landscape of solutions in a single computational step. But to harness this incredible power, we have to create one of the most extreme environments on Earth. These machines can only think when they are frozen to temperatures colder than the vacuum of deep space. The speed of these machines is not just a theoretical promise. It's a demonstrated reality. In recent experiments, quantum computers have been tasked with solving incredibly complex, specific problems designed to showcase their power. One such problem is called Gaussian boson sampling. It's a mathematical labyrinth so convoluted that it's effectively useless for anything practical, except for one thing: proving how fast a quantum computer is. China's Jiujing quantum computer solved a complex version of this problem in a single microsecond. A microsecond 1/1,000,000th of a second. The world's fastest classical supercomputer, the Fugaku in Japan, was tasked with calculating the same answer. Its estimated time to completion: over 30 trillion years. Let that sink in. A task that would take our best technology longer than the entire age of the universe was completed by a quantum computer in the time it takes for a camera flash to go off. This unfathomable speed has led to some wild, fascinating speculation that pushes the boundaries of science fiction. Some physicists and computer scientists have cautiously suggested that this power is so immense, it defies explanation within our single universe. One fringe, yet intriguing, hypothesis is that these quantum computers aren't just calculating in our reality. They speculate that through the phenomena of superposition and entanglement, these machines might be tapping into a vast network of computational resources from parallel universes, running the calculations across countless alternate realities simultaneously and collapsing the results back into our own. Whether you believe in the multiverse or not, the implications are staggering. We are building machines that operate on a level of reality we are only just beginning to understand, unlocking a computational power that could solve humanity's most intractable problems. So if these machines are so powerful, why don't we have them on our desks? Because for all their godlike potential, qubits are unfathomably fragile. They are the shyest geniuses in the universe. Their delicate quantum state, the superposition that gives them their power, can be destroyed by the slightest disturbance from the outside world. This loss of quantum state is called decoherence. Think of it like trying to hear a perfectly clear, whispered secret in the middle of a roaring rock concert. The noise of the concert, any vibration, any stray magnetic field, any tiny fluctuation in temperature will drown out the whisper instantly. For a qubit, the normal temperature of our world is that rock concert. The simple thermal energy of atoms vibrating at room temperature is more than enough to knock a qubit out of its superposition, turning it back into a mundane classical bit. Its magic vanishes. This is the single greatest engineering challenge in quantum computing. The solution? We have to create the quietest, coldest, most isolated place in the universe. We have to freeze them. Companies like IBM have built extraordinary cryogenic refrigerators, like the GoldenEye, that cool their quantum chips down to 15 millikelvin. That's 15 thousandths of a degree above absolute zero, the theoretical point at which all atomic motion ceases. To put that in perspective, the average temperature of deep space, the vacuum between galaxies, is about 2.7 Kelvin. This means the heart of a quantum computer is more than 100 times colder than the coldest reaches of outer space. It is only in this profound artificial stillness, shielded from the noise of our world, that the quantum whisper can be heard and the true potential of a quantum AI can be unlocked. Despite the immense challenges, the progress in building these machines is happening at a breathtaking pace. We are in the middle of a hardware revolution. Take China's Jiujing 3.0 quantum computer. It operates not on superconducting circuits like IBM or Google's machines, but on photons, particles of light. In a recent breakthrough, it solved a complex sampling problem 1,000,000 times faster than its predecessor, Jiujing 2.0. By successfully detecting 255 photons in its experiment, it pushed the boundaries of computational complexity far beyond what was previously thought possible. This isn't just an incremental improvement. It's an exponential leap, showcasing how quickly the field is evolving. This demonstrates that there isn't just one path to a quantum future. Researchers are exploring various physical systems to house qubits, superconducting loops, trapped ions, silicon photonics, and even synthetic diamonds. Each approach has its own strengths and weaknesses in the fight against decoherence and in the quest to scale up to more and more powerful machines. What we're witnessing is a Cambrian explosion of quantum hardware, a period of rapid and diverse experimentation that is accelerating our journey toward a truly functional, large-scale quantum computer. This technological explosion has ignited a fierce, global competition that many are calling the new space race of the 21st century. The stakes are nothing less than global economic and strategic dominance for decades to come. The starting gun arguably fired in 2019, when Google's Sycamore processor officially achieved quantum supremacy. This was the milestone moment where a quantum device performed a calculation that would be practically impossible for even the most powerful classical supercomputer. The race was on. Since then, the competition has only intensified. IBM has consistently pushed the boundaries with its own chips, like the massive 1,121 qubit Condor processor and its ambitious roadmap to build a 4,000 qubit machine. Simultaneously, China has made quantum a national priority, pouring billions into research. Their Zhuchongji superconducting quantum computer has also demonstrated staggering performance, reportedly performing calculations 1 billion times faster than Google's Sycamore on certain tasks. This isn't just about scientific curiosity or national pride. The first nation to develop a large-scale, fault-tolerant quantum computer could gain an insurmountable advantage in key areas. They could design new materials, create revolutionary medicines, and, most critically, break nearly every form of modern encryption that protects our global financial systems, government secrets, and military communications. This is a race for the master key to the digital world, and no one can afford to be left behind. While the race for quantum computation rages on, a parallel revolution is already on the verge of changing our daily lives: quantum communication. The promise here is simple and profound: a truly unhackable internet. It works on a principle called quantum key distribution, or QKD. Imagine sending a secret message sealed with a quantum lock. According to the laws of physics, the very act of a hacker trying to observe or pick that quantum lock would instantly change its state. This change is immediately detectable by the intended recipients, who would know their communication has been compromised and can discard the key. It's the digital equivalent of a letter that bursts into flames if anyone other than the right person tries to read it. This isn't science fiction. China is on track to launch the world's first commercial, secure quantum communication network in 2025. Led by Chief Scientist Pan Jianwei, a pioneer in the field, this network will provide unhackable systems for critical sectors like finance, government, and electronics. Pan predicts that within a decade, quantum communication will be deeply integrated into our daily lives. Imagine a future where your bank transfers, your private messages, your medical records, and your vote are all protected by the fundamental laws of the universe, making them mathematically impossible to intercept without detection. This is the first wave of the quantum revolution, and it's about to wash over us. Now, we arrive at the ultimate destination. What happens when we take the truth-seeking AI we dreamed of in the beginning and merge it with the infinite processing power of a mature quantum computer? The result is quantum AI form of intelligence so far beyond today's models that it's difficult to fully comprehend. This fusion promises to ignite a new renaissance of scientific discovery. In medicine, a quantum AI could simulate the trillions of ways proteins can fold in the human body, solving the mysteries behind diseases like Alzheimer's, Parkinson's, and cancer in a matter of hours, not decades. In materials science, it could design new molecules from the ground up, creating room temperature superconductors for lossless energy transmission, or revolutionary battery technologies that could solve our climate crisis. In cybersecurity, it would create an AI-powered defense system that could not only use unbreakable quantum encryption, but also predict and neutralize threats before they even happen. And perhaps most profoundly, it could lead to human-like assistants that are more than just clever chatbots. An AI that can grasp true context, nuance, and even ambiguity by holding multiple conflicting ideas in superposition, much like the human mind. An AI that doesn't just process data, but understands meaning. This is the end goal. An intelligence that doesn't just answer our questions, but helps us discover new questions to ask. An AI that can tackle the fundamental mysteries of the universe, from dark matter to the origins of consciousness. Because it can think in the native language of the universe itself, quantum mechanics. And so, we are left with the ultimate question. Is this awe-inspiring, world-altering fusion of AI and quantum computing something we will witness within the next decade? Or will it remain the stuff of science fiction for generations to come? We are building a new kind of mind, frozen at the edge of absolute zero, that holds the potential to solve our oldest problems and unlock a future of unprecedented prosperity and understanding. The journey is fraught with immense technical challenges and profound ethical questions, but the race is undeniably on. As we stand at this crossroads, it's worth reflecting on the lessons this journey teaches us. First, the profound importance of our guiding principles. As we build these godlike tools, the initial plea for a truth-seeking AI becomes more critical than ever. The power we unleash must be anchored to a foundation of integrity. For our own lives, this is a reminder to always question, to seek the underlying truth, and not to be swayed by the most popular or plausible-sounding answer. Second, the power of thinking differently. When classical computing hit a wall, the solution wasn't to push harder on the same path. It was to leap to a completely new paradigm. In our own lives, when we face an insurmountable problem, sometimes the answer isn't more effort, but a different perspective. Don't just try to build a faster horse. Dare to imagine a car. Finally, a lesson in humility. We are reaching for cosmic power, yet our tools, the qubits, are so fragile they must be shielded from the universe itself. It teaches us that great ambition must be balanced with great care, deep respect for the forces we're working with, and an understanding of our own limitations. So I leave you with a few questions to ponder. If you had access to a quantum AI for one day, what problem would you ask it to solve? Does this future fill you with more excitement or with apprehension? And what steps should we, as a society, take today to ensure this power is used for the benefit of all humanity? Thank you for joining me on this journey into the frozen heart of our digital future. I hope it has sparked your curiosity and left you with a sense of wonder. If you enjoyed this exploration and want to dive deeper into the technologies that are shaping our world, please like this video, subscribe to the channel, and hit that notification bell so you don't miss our next adventure. We'd love to hear your thoughts in the comments below. Until next time, stay curious.